So the output that we get if we return out of the remote desktop, it looks like this. So as you can see here, this is the output, all the data, and it's kind of in an unreadable format right now. So within the project there was this post-processing Python file. So it reads in the data and then puts it into nicer columns with descriptions. So we have the time, the channel for the transmitter and the receiver, and different kinds of information. Most importantly, the delay, the Doppler, and the different multi-path delays. Now, one thing they had to do was remove anything that had to do with node 0 because we only wanted node 2, because we only wanted transmitter and receiver data. And once you do that, this is where we're looking at so far. The next thing we had to do is calculate the total delay. If you look here, the main delay is these blue dots, and then if you add that with the multipath 1 or 2 delay, you get these green or orange. So you want to get the full delay time it takes for your transmitted waves to return to the receiver. And for reference, then, if you have this delay, this is what it looks like. This is what a single delay curve looks like. So since it's less time with this y-axis being the range, and this over time, so since it this is the delay, not the time, but since the delay is calculated to be less, we know the object is closer and is moving farther away. Now, what they did to introduce multi-target tracking is they took this initially calculated simulated object, and then what they did was using that data, they created a second simulated object. So we have one here that's moving in the opposite direction as our initial object. And so this is what the simulated data just looks like, with the orange being one track and another one being another track. And then that they also calculated the total delay in this column, removing it from the multipath delays, and they also have a Doppler shift frequency of 351.67 Hertz that they added, which we'll use later to calculate the velocity. So this is all written to a text file, and the problem with this text file is that the format is very different from what we actually need. So again, this is the output of our data of what we just ran in simulation. However, what the simulation for the multi-target tracking filter expects is something much along the lines of this. At the time, it expects the range and the velocity of a detected object, and this is normally what would happen if we put it through a hardware emulation. However, since we're doing purely in simulation and we're not doing any hardware channel emulation, we have to figure out a way to not only convert the layout of our data, but also to get the velocity and range, because that's not something that was calculated during the simulation. In reality, that's something that would be calculated through the radio in the hardware emulation. To do that, we wrote this Python script. So it reads in the data from our text, and again, we can see it all here. The first thing it does is calculates the velocity, and while velocity isn't too important in the context of our simulation, since all of our graphs are a range versus time graph, we did figure it would be appropriate. So using the equation of the Doppler shift frequency being 2 times velocity times the cosine of the angle of the target divided by center wavelength, where here it's cosine of 0 since we're in direct line of sight of target. We arranged it and we got the equation that the velocity is equal to the Doppler shift frequency times the center wavelength. Here the center frequency was 4 gigahertz, so we just divided that by the speed of we had the speed of light divided by that center frequency to get the center wavelength. We divided that by 2 and we got the velocity. And so the velocity is all the same for all of them at the moment, because this is a rather simple calculation, but we calculated it to be 13.1785 meters per second. We also had to calculate the range, and how we did this was we took each of these delay values, and we did a very simple calculation again, where we just did the speed of light times the delay, and then just divided that by 2 to get the range. And doing this, we got this output of range values. As you can see, these are like every other, so this is like one track, and then here's another one. As we end up, they end up in opposite places. Now this is a function I had to add fuzz. We'll explain that in a bit later, but since this is a purely simulated environment, it is fairly easy to get good results. So we'll come back to this in a bit, but then we write this output, and now if we look to sim data parse, we have this newly formatted and the correct velocity and range data at the correct times. So now if we go to our JPTA simulation, which also had to be slightly rewritten to account for no emulation, we have our imports. This is what's, again, our data looks like. So without knowing which track is which, this is what the data that goes into the filter looks like. Now, of course, this is purely simulated data. There's no emulation or any real-world occurrences here that are making the data a little bad. So when we do our multi-target tracking using JPDA, we can see that it does a fairly good job at tracking which track is which, because we knew beforehand that this was one track and this was another track, and the multi-target tracking gets that exactly. So one thing I did was add this fuzz. So for example, we can add a small amount of fuzz. This essentially takes your simulated data and changes the value a little bit by a factor of -1 to 1 times your fuzz value. So 0.3 is fairly small, if we write that to the output, and we do see the values here are slightly different than the original ones. And if we go through and run it through again, we can see there's a little bit more variance, not much since we only did 0.3, but the filter gets a little worse at tracking it, of course, because there's more variance. But by using this, we're able to test the filter a little more. And this is just our basic example with 2 tracks, but we, as you'll see in the presentation, we did do different track lengths as well as adding a 3rd track in to see how the multi-target tracking would cover.